my son Glenn Collins for doing this video. It's about a talk that I gave at Marian University virtual talk on October 3rd, 2020. Marian University in Indianapolis, Indiana was a host to the MAA, Math Association of America meeting, the Indiana section. My name is Dennis Collins, and I'm a retired professor from University of Puerto Rico in Mayagüez. Graduated from Illinois Institute of Technology in Math, PhD in 1975. Anyway, the title of this talk is Convexity of Symmetry Measures for Discrete Endpoint Patterns. And I have my friends from the Bust Museum in Knox that I have Isaac Newton and Albert Einstein. So this is based on my symmetry patent of 2011, and that goes back to the 2007 article in the General Systems Bulletin, volume 26. Anyway, we're interested in the difference between growth that's not convex and convex growth. Convex growth is basically U-shaped, something like this. And according to the symmetry pattern, you can calculate the maximum symmetry of endpoints. And the maximum symmetry is a fourth degree polynomial, which is equal to n plus 1 times n minus 1 times n minus 2 divided by 8. There's something called the second derivative test for convexity, which is if the second derivative is positive, then the function is convex or has a U-shape. In this particular case, you can directly calculate the second derivative of this fourth degree polynomial, and it comes out to be 2 times minus 1 plus 6x plus 6x squared, which is a quadratic which has two roots, approximately minus 1/6 and plus 7/6. So we can plot this function, and we see that beyond about 7/6 it stays positive. So that means that the maximum symmetry of endpoints is going to be convex if you get beyond 2, because it will just keep going upwards. So what is the point of this thing is to show that many patterns of growth as you increase endpoints are not convex, but the maximum growth of symmetry is a convex function. So somewhere as you get better organization, you will get towards the convex function. There's sort of a playing field for this project, which I will try to explain. First of all, you can have a three-dimensional graph, which is this thing, and along the x-axis, and then there's the y-axis and the z-axis. The x-axis is the number of points n. The y-axis is the symmetry, and the z-axis is what's called the simplexity, which is the symmetry times the quantity maximum symmetry minus symmetry. And we find that there is this function that I just talked about called maximum symmetry, which is a fourth degree polynomial. It will go up like this, and it's very close to the y-axis because a fourth degree polynomial goes up very quickly. So according to this symmetry measurement, if points are completely random, the symmetry is 0. So along this axis, as n increases, if there are only random points, then the symmetry measure will just stay 0. How can you tell if points are random or not? You can check whether or not there are equal distances between pairs of points. So if we look at just quickly some graphs of sets of points, you can find out that the more pairs of equal distances between points there are, the more symmetry there is. So, for example, the number of pairs of equal distances in a regular pentagon is 20. There's equal distances between the points around the pentagon. There's some equal distances around straight lines that connect triangles around the pentagon. And there's a combination of 5 things, 2 at a time, of these points. And then there's the star-shaped distances. There's a combination of 5 things taken 2 at a time, which is 5 times 4 over 2 times 1. There's 10 equal distances on the distances of like points on a star. So the total symmetry is 20 in this case of a regular pentagon. A simpler thing is a parallelogram, and in that case there's one pair of equal distances here and another pair here. So there's basically less symmetry because there's not as many pairs of equal distances. Well, anyway, going back to our chart here, if there is more symmetry, it will gradually go along towards higher symmetry along the y-axis. And if you draw lines from 0 symmetry up to the maximum, you'll see that as n becomes larger, it goes up to a 4th degree polynomial, which goes around this way. So what can we say is that along the maximum symmetry, it will have this 4th degree polynomial n plus 1 times n minus 1 times n minus 2 divided by 8. So somewhere between here and here, if you will have a function that becomes convex versus the number of points. And along this boundary of this maximum symmetry, the actual in the maximum symmetry, the number of equal distances will be this quantity, this polynomial. So the entropy of that will be 0 because all of the distances, if you put every point at the same point, all the points will be concentrated on 0 distance between each 2 points, which is the same distance. And if all the points are the same distance, 0, then the entropy is 0. So along the maximum symmetry point, the entropy or disorder is 0 because there's a maximum of symmetry. And along this point, the entropy is something like n times log of n is the maximum entropy. So along one side there's maximum entropy, and on the other side there's maximum symmetry. So it goes from maximum disorder to maximum order, which is this fourth degree polynomial. And we know that if you get along here, there's convex growth. So what we want to show is that if you're over here somewhere, there's not convex growth. So we can look at say a two-dimensional growth pattern. So here's the picture of a two-dimensional growth pattern. This is, say, a 5 by 5 grid where each point is equally spaced in this. Well, here's the 5 by 5 grid. Anyway, you can calculate the symmetry of these patterns, and you find out that if you take one point away from the corner, there's not as much symmetry. It looks like something's missing there, a missing point. Anyway, the symmetry of that would be 3736. That has 24 points. There's the 5 by 5 grid, which has 5, 10, 15, 20, 25 points. And you can calculate the symmetry of that as 42, 42. Then you can start building up to a bigger grid, like a 6 by 6 grid. If you add another point here, there will be 26 points, and the symmetry of that will be 4698. So you can ask if this kind of growth, that is starting with lesser points, going up to a square grid, and then getting up to more points, is a convex growth or not. And in this case, a convex function has a property that if you draw a straight line between the two endpoints and look at the middle point, the function will be always below. In order to get the U-shaped growth that we're talking about over here, the point symmetry at this point would have to be less than this straight line. So this point on the straight line is actually the point 25, 42, 17. So in order to be convex growth, the 5 by 5 would have to be less than that. Have to be less than 4217. But actually you can calculate the symmetry of the 5 by 5 pattern is actually more than this midpoint of this straight line, which is 4242. So we conclude that two-dimensional grid growth is not convex growth. And we have here what I call the square grid completion bulge. That is, as you gradually fill out a square grid, it sort of looks like there's more symmetry than what there should be if you would have convex growth. So the question is, can you get some kind of better organizing principle than two-dimensional growth that would somehow become convex and have the U-shaped pattern instead of this bulge. So there's sort of like a physical interpretation of this, that the square grid looks like it's more symmetric, or has more symmetry than if there's a missing point or an extra point. So as I say, usually if you study things like in architecture, you find that if there's like missing points, like there's a break in the wall, or if there's extra points, like the line isn't straight, it will look like it's less symmetric than if you have a perfectly square wall, or a straight line. Or, well, the question is, could you go to three-dimensional growth, like three-dimensional stacking of grids? So it turns out that you can get more symmetry by going to a three-dimensional pattern instead of just a two-dimensional pattern. And the question is, what about this higher dimensional growth? Would that become convex growth? Anyway, going back to our original pattern, it turns out that here, back to here, you can get some idea of how the amount of growth by multiplying the symmetry by the maximum symmetry minus the symmetry, which gives you a parabolic shape as you go up. I guess this is a mistake in the graph here, but anyway, you get sort of a ridge going up. And so the simplexity is sort of like the most complexity you can get. So on either side of this thing, on one side it's too simple because there's only random points, there's no pairs of equal distances. And on the other side there's the maximum symmetry, in which case the entropy is zero, there's no disorder. So both of these border lines are sort of boring. And in terms of like natural growth and biology and so forth, the interesting things occur, say, sort of halfway from one side to the other, which is the maximum of these parabolas, which is going to occur at basically well, halfway across here, and the maximum is 1/4 of this thing squared. Well, anyway, there's a question then of what kind of growth does biology have? And you can show that something that Arthur M. Young studied, that it's a straight line has a certain amount of symmetry, a grid has more symmetry, a three-dimensional stacking has even more symmetry, and so forth. A fourth-dimensional symmetry, you can imagine something like well, a three-dimensional symmetry you can think of as a cube, like a salt cube. Fourth dimension, you could imagine something like a marching band, where the fourth dimension is time. So if you think about a marching band, there's an equal spacing between all the people that are in the band. So there's a certain amount of equal spacing there. And then there's like a beat to the band as it plays, that the regular beat, like 1, 2, 3, 4, 1, 2, 3, 4. So there's equal spacing in time. And talking about videos, a video can be considered as some kind of a fifth-dimensional object, where you can study how four-dimensional optics change. So you can take a video of the band and show that Mr. X is out of step all the time, and so the symmetry isn't as good as it should be. And by studying the video, you can see how to increase the symmetry by making sure that Mr. X is in step with the rest of the band and so forth. So anyway, at some point, as the dimension increases, you'll reach this point of diminishing returns where things get more boring and everything is basically at the same point. So the question is, and also somewhere as we go along here towards increasing symmetry, there's going to be some point where instead of not being convex like the two-dimensional growth, the organizational principle will give you a convex growth. So the question is, studying the different principles of organization of points and seeing where they become convex. Of course, if it becomes maximally convex, that will be like all points at the same point or some place, so that, or another possibility is that you can have what are called unit vectors in like n-dimensional space will all be the same distance apart. But anyway, having maximum symmetry is more or less like boring. So there's somehow the fact that this symmetry bulge, the symmetry completions square bulge, is more interesting and more likely to occur in biology. That is, things that don't have broken legs sticking out and so forth are going to survive better than things that have sort of perfect symmetry. So the most perfect forms of animals have sort of like interesting symmetry. But anyway, the point is to study convexity versus the number of points to see biologically where this bulge occurs. That gives you the most interesting things. Well, that's the basic question to study. There's very many mathematical interesting points here. For example, figuring out what the symmetry is of a perfectly square grid. So even that is something I haven't been able to calculate yet. And so there's like many mathematical problems in this. In the case of the symmetry growth, you have the possibility of Pythagorean triangles, so you can get more equal distances. If I go back to this, well, just to summarize this, let me say there's a symmetry patent, which is a way of measuring symmetry. There's the playing field, which is this thing with the complexity. You can show that maximum symmetry does have a convex growth. You can show that other organizing principles like square grid pattern does not have convex growth. So the conclusion is that you need more organizing principle for convexity, but there could be punctuated equilibrium, like where you have one-dimensional things becoming two-dimensional. It will have a greater evolutionary growth when you go from one dimensions to two dimensions, or two dimensions to three dimensions, or sort of a marching band is like a maximum of organizing principle in our world. But anyway, as I just mentioned, this part is partially covered in my book, Conflict in History, Measuring Symmetry, Thermodynamic Modeling, and Other Work by Dennis Glenn Collins, in 2011, published by Author House in Bloomington, Illinois. Well, thanks for listening to this talk. And as I said, there are many interesting mathematical questions involved. Thank you, and thank you to my son for recording this video.